work is some cooperation within our university in Dortmund, so located in Germany. So I would like to introduce Professor Walter and also the colleagues from the Institute of Machining Technology. We are going to provide the specimens that we investigated. I'm from the Department of Materials Test and Engineering. So my talk will deal with the scientific information behavior of this internal threads and profiles, and it's some kind of light research. So as you will see, I want to deal with standard geometries, as I always show you in the following slide. So after giving you some slide for motivation, I'm going to show our testing strategy, as it's also shown here on the slide. And then I will come to the results for quasi-static and fitting behavior and how we correlated these with the profile qualities. Okay, to get your attention, I will show some short video about the process on how the material for our specimen is manufactured by the colleagues. And as you see, there is a rotating tool that penetrates into thin-walled materials, and for terms due to the friction and the high temperature, the material is expanded. And there, in this standard application, there is some bushing to, in the second step, manufacture a thread with the largest thread depth than the profile thickness. So this is an advantage of this procedure here for friction drilling and threading. And in our case, the whole thread is formed chipless, so the friction drilling and the thread forming manufacturing process is chipless, so only forming. So you can use this for different kind of materials, and as I told before, so here on this slide is also the manufacturing process showed, and in our investigations we deal with magnesium and aluminum alloys, so lightweight materials, and yes, our cooperating institute is manufacturing these threads with this new kind of application, so the cross-sectional area of these thin-walled profiles are manufactured, and this leads to some kind of applications for automotive industry, like this frame structures here, as you can see. And as our goal for this work was to characterize the mechanical properties of the friction-drilled internal threads. So at first, to show you microstructure of the materials that we got. So this is as delivered casted alloys, so there's nothing special to talk about. It's used in as delivered conditions and it accords to the standards. So alsi10mg and az31 aluminium and magnesium alloy. So I show you here the specimen geometries that we used. So as I told you, thin-walled profiles. So we, in the first stage of this project, correlated the wall thickness of the specimens with the mechanical properties. And here you can see an example where the wall thickness is about 5 millimeters. And yes, it differs in the investigations from 4 to 8 millimeter. And here is also shown yes, the internal thread with a nominal diameter of 6. So the nominal diameter is even larger than the profile thickness. And here is also shown yes, an image of such specimen. And in contrast to that, the magnesium alloy has the same nominal diameter in the thread. But as you can see, there are some differences in the dimensions. And this is due to the dimensions of the casted sheet. So what we're going to see is these manufacturing techniques, chipless forming, so friction drilling and thread forming. Okay, coming up with a testing strategy. So our experimental setup is given here. And as you can see, we used a servo-hydraulic testing machine where the specimen is connected to a threaded rod with a counter holder. So steel counterholder and a steel threaded rod to apply the mechanical stress. And the screw in depth was 4 mm for every specimen, so this was constant. And tensile tests and fatigue tests were performed, so tensile tests strain with the strain rate, so strain control tests and fatigue tests were performed load control. So the load increase test that is here given is shown in the next slide. And during the test, we adapt the specimen or the system in this case, because the threaded rod is also part of the system with different measurement techniques. So for strain or stress strain hysteresis measurements, we applied an extensometer, mechanical extensometer, and also for deformation-induced change in temperature, we applied K-type miniature thermocouples. And as you see here, they are connected by drill holes and little notches to the top of the threaded rod. And as you can imagine, the threaded rod is here 4 mm underneath the specimen surface to get access to the special areas of the specimen, so to be in a part of the specimens. Okay, the principle of fatigue testing is the instrumented continuous load increase test. So what we do is we perform mechanical testing in load ratio of 0.1. So there's a tension load range and with a frequency of 10 Hz, and we start at a quasi-damage-free amplitude, and we rise the amplitude during the test continuously until failure of specimen. And what we are trying to get out of our measurement techniques that are adapted during the test with specimen has some fatigue properties during this load increase. And the first one is, of course, the failure amplitude, the force amplitude at failure, the fracture of the specimen. And the second one is, if we analyze the material response of our measurements, then we have transition point from nearly linear slope to an exponential slope. Okay, then first we come to the quasi-static results. So here a force total strain diagram is shown for two kind of specimens. So in red the magnesium specimen and in blue the aluminium specimen, and wall thickness was 5 mm. So what we did, we compared the maximum forces in the test and compared them with the wall thickness of specimen that was tested. And as you can see, we got linear regressions between maximum force and wall thickness that are have a very high correlation coefficient. And as a result, as first result, maximum forces of magnesium alloys are higher than those of aluminium. And to show you an example of the results of a load increase test, here is magnesium specimen with a wall thickness of 8 mm, and this is our control parameter, force amplitude and maximum force respectively. And the first value that we can get out of this test is the maximum force at failure, as you can see. And here are given the curves for the plastic strain amplitude out of stress strain hysteresis loops and the change in temperature for the specimen. And as you can see, and as I told before, there is a transition point from the linear slope to the exponential slope in both cases. And we can get out an estimated fatigue limit for the specimen and for these materials. So this is shown as a very easy way to do it, but of course, in fact, we use mathematical logarithms for that to get the special value here for the estimated fatigue limit. And if we estimate the fatigue limit, of course, we have to validate them in constant amplitude tests. This is not what we've done till now, because the project started at end of last year. So we're going to do this, of course, but we can show in other works that it works for this kind of friction-drilled aluminium alloys and also for magnesium alloys for standard material specimen. So now I will only concentrate on the maximum force and failure, and this is also correlated over wall thickness of the specimen, and you can see the nearly same regressions here as we've seen in the tensile test. So as a result, also the magnesium alloys have higher values than aluminium alloys. Okay, then we wondered how we can correlate this with profile qualities. So in fact, the first thing is have a look on the dimensions of the manufactured specimen, and there's a difference in diameter. So lengthwise and crosswisely, it is about 13% for aluminium alloy, and the difference in diameter for magnesium alloys is nearly negligible, about 2%, and this is the reason. So aluminium alloys have oval forms of core holes due to the manufacturing process of friction drilling. Yes, the second slide, therefore, for profile qualities is, of course, cross-sectional areas. So we investigated the quality of the threads. So on the left side, the aluminium alloy, and on the right side, the magnesium alloy. And as you can see, we got rugged surfaces for both specimens. But the difference here is these characteristic claw shapes that are formed during the process, during the forming process, and the magnesium alloy has nearly closed claw shapes, so there is more material in contact with the threaded rod than from aluminium alloy. Okay, and at last we had to have a look at the specimen surface after the fatigue testing, because as you can see here on the left side, for aluminium alloys there was no difference in contrast to the manufactured specimen, so manufactured specimen, and in contrast to that, the magnesium alloy showed some cracking on both sides of the specimen, and the distance from these cracks to the surface of the specimen was about 4 millimeters, so this corresponds to the screw-in depth of the threaded rod. And the threaded rod here was movable after the test, and on this side it was not movable, so there was some kind of shear of the material, and this is what we also investigated for the tensile test. So if you push out the threaded rod, then you have like spherical at the threaded rod. Okay, let me shortly sum up. We had done some mechanical investigations in internal threads in aluminium and magnesium thin-walled profiles, and we developed a test setup with optimized sensor systems, so the fatigue limit could be reliably estimated in continuous low increase tests. As I told before, this is to be validated in constant amplitude tests. Maximum total loads increased linearly with increasing wall thickness of specimens, so in tensile range and this fatigue range. And the aluminium specimens were about 20 to 24% lower in quasi-static and 37 to 47% lower in cyclic range in comparison to magnesium specimens. And the correlations with microscopic investigations so far show that aluminium specimens had oval forms of core holes after friction drilling, so we have incomplete profiles after thread forming in crosswise direction. And the threads show characteristic claw shapes, and in case of magnesium specimens, they were nearly closed. So in the last slide, we have seen different failure mechanisms in load increase tests, and magnesium specimen had surface cracks, what is of course to be investigated in further investigations. So acknowledgement for German Research Foundation for this project. And thank you for your time and your attention.
Thank you. questions? Comments?
Is there any like heat affected areas, or do you have to do any stress relief, or is that going to be further research from the friction drilling?
So you mean if there's, so at first I've not shown some microstructural changes during the friction drilling, because this is very important for us to investigate, of course, work hardening effects and stuff. So we will have to correlate this with microstructure and micro hardness along the threads. So is this going to this direction?
Yeah.
Any other questions? Comments?
So please excuse that there was no correct initiation and growth and stuff, but maybe this is going to be the next mark then.
Okay. In Belgrade in 2 years then. Okay, I think that it's coffee time with the service. I would like to thank you all for being here, and of course thank you to our speakers for the great talk.
Hello. Thank you for your nice presentation.